Okay, great. All right. Welcome, Dr. Kastner. Thank you so much for coming. If you could just start us off with the university and college you teach, the department, also give us an explanation of your field.
I'm a professor of neuroscience and psychology, and I'm in the Princeton Neuroscience Institute at the Department of Psychology at Princeton University. What I do is, I'm not a psychologist, actually that's not my background. My background is in medicine and in what's called neurophysiology. The field of neurophysiology is a field that tries to understand how the brain works, basically. So what are the brain mechanisms that give rise to our seeing, hearing, to all of our different senses, and also to what we call cognition. So how can we use our brain to produce speech like I do right now, or to produce thought, and so on and so forth. And that's basically what I try to do, at least in small parts, in the Princeton Neuroscience Institute, together with a lot of our colleagues.
I see. So how long have you been a professor?
I've been a professor at Princeton University for 21 years. So I started there as an assistant professor and made my entire career at Princeton University. Yeah, it's a wonderful place with a lot of resources. So once you're there, it's hard to part from there.
Right. So do you have any outside hobbies or interests?
Oh yeah, quite a few actually. I like to be in nature. I like to hike and to bike. And I'm a drummer, so I drum every day actually. I also play various guitars, but my interest in music right now is in drumming. It's all, rock music, jazz, blues, and so on. I discovered during the pandemic ceramics. So I go to work in a ceramics studio on a regular basis. And I exercise with Pilates.
Oh,
And I have two kids, so they take some time too.
I see. You're so diverse. I love that. So many great things. All right. So let's start off with this. So what led you into your field of study? And let's say, where do you think it's going to go in the future?
So my career started, I'm a native German, and my entire education was in Germany, which is very different from the American system. So it's a public education system, and students there have an enormous amount of opportunities. I was very fortunate to take advantage of that. I was a first generation student. Actually, I was the first in my family to graduate from a high school. And due to that, there was no mentorship. There was no one who would guide me what to do next. And my parents actually wanted that I should become a finance accountant and basically check on other people's taxes because I was good in math. But my teachers at the time, my high school teachers, two of them, they convinced them that it might be good for me to go for a higher education degree. And in high school, I was really not interested in life sciences at all. And I decided to study philosophy and history. Those were my passions at the time. And through philosophy, I got into brain science. So I attended a lecture that's back in the mid 80s, long before you were born, by, at the time, a very, very famous German neuroscientist who talked about the intersection of the field of neuroscience, of brain science, and the questions that the field of philosophy was asking. And to me, that was absolutely intriguing. So it was just eye-opening to understand that the questions that I had about, how do we become aware of ourselves? How do we reconstruct from what we take in our environment? How would a robot do that, right? How would the machine do that? And how does that compare to how we do that with our brain? So it was really eye-opening to understand that I could approach this by doing experiments, by designing experiments directed at specific questions, and not just by basically thinking and arguing about that. That's what a philosopher at the time at least would do. And that completely changed my mind about what I wanted to do with these questions that I had. And I decided to change fields, and I wanted to study neuroscience, which at the time was not so straightforward. So these days, a young student would apply to a graduate program in neuroscience, and there are plenty of those programs, and they are wonderful. But they did not exist at the time. And in Germany, if you wanted to become a neuroscientist, you had to go to medical school and become a medical doctor first. And that's what I did. And then I did my PhD in neurophysiology, basically simultaneously with the MD, with a medical school. And this is how I got into that field, but it was basically clear for me from the outset that it was very unlikely that I would become a practicing physician, but that I wanted to get into science, and that's what I did. And after my PhD studies, I was very, very fortunate to go and receive training at the National Institutes of Health in Washington, D.C. Mm-hmm. And there I learned the techniques that I later implemented at Princeton to study the human brain. And this is basically what got me here. So it was a little bit, I'm a big Beatles fan, as you can see. It was a little bit a long and winding road, to speak with one of the Beatles' famous songs.
I see, that's great.
You also asked me where the field is going. Do you want to get an answer to that too? It's probably even longer than the first one. So, so my field actually, so I study vision, and later on, one of the problems that has particularly interested me is how we select visual information. So our environments that we live in, our visual environments, are extremely rich, and there are many, many objects present at the same time. And so the question that I had very early on was, how do we represent that information? There's just so much to represent. Or is the brain basically just throwing out a lot of it, up front, basically, so that you don't have to deal with all that noise in the environment? And so this problem of how we select information, we refer to that as attention, and that's more of a popular term that people understand intuitively. How do we attend to things in the world? That was a question I had very early on. And when I started to study these questions, the way we were viewing at the time in our textbooks and so on, the process of vision was like cameras. Our brain, our visual part of the brain would act like a camera, take in all that information. And then, some magical higher order centers would make sense of it. And, and eventually select what interests us and filters out all the rest. And that has dramatically changed. Now vision is viewed as a very active process from the very outset. So our brain basically is creating an image of our environment, and what we take as physical inputs from the environment is relatively little. And that has been very transformative, I think. And so these ideas of basically how our brain creates a reality around us and what the limitations of that process are, I think it's one of the examples of what will be very, very interesting in the future.
Mm-hmm. Great, that's awesome. All right, so speaking on the questions you're answering, let's just dive into any research that you're doing. So you can go deep into this if you like. So basically, what questions are you answering in your research? If you did anything in the past, probably anything you're doing right now, and also like any data or latest findings in your lab.
Yeah, so that's a great question. So when I started out, I was interested. So I studied the human brain at the time, and I used what we call functional brain imaging methods. So you can use methods with any normal magnetic resonance imaging scanner. So these are scanners that from any hospital where people typically just take anatomical images of their brain to make sure that everything, it looks good. So that's what you do in medicine, or as a patient if you get a brain scan. But as scientists, we can use these brain scanners also to take what we call functional images of the brain. That means we can activate specific parts of the brain that get involved in specific tasks. So for instance, if I attend to your face right now in this conversation, there are certain areas in my brain that get really, really excited about this, and they will get heavily involved. And these would be, for instance, a face perception network that we have in the visual part of our brains. And it would also be our attention network. And my early work, after I started here in the early 2000s in Princeton, was all about characterizing what that network is. So which parts of the brain get involved while we are attending to take in visual information. And the second big question at the time that we had was, at which point in this large network structure that we identified do we filter information? So traditionally, filtering is probably the most important thing in attention research. It's as important as selecting what interests you, because typically you have to deal with a lot of clutter and noise. And how do you get rid of it? And traditionally, people had thought that this was like a high-level process. So it's, somewhere in the front of your brain where, a lot of the human-specific abilities happen. That's where the filtering is happening. And we showed at that time that it's actually an early process. So very early in that visual processing stream that's happening, you just get rid of most of what is not of interest. And then the brain just basically deals with what's important.
Is this what's called selective attention?
That's what's called selective attention.
Mm-hmm.
So those were that was the early work in the human brain. And one discovery that we also made early on was that very old brain parts that are buried deep under what we call the cortex or the neocortex. So that's all the structure that has these windings. And they are deep parts that we share with many, many other mammals who do not even have such a neocortex. These brain regions are called the thalamus, or one part of these subcortical structures is the thalamus. And we saw very early on that there were cognitive signals, so signals related to attention in those old brain structures. And that was very interesting to people, because many people had thought, oh, these are old brain structures. They are not doing anything fancy. They cannot have anything to do with it, cognition, because that is basically what the primate brain stands out by. And we basically showed that that did not seem to be true. And following up on that, I turned to do work that, so I have to tell a little bit probably about the method. So up to that point, the first 10 years at Princeton, I did a lot of brain imaging to look at these networks and kind of get an idea of what the different networks part were doing. But imaging is a technique that tells you a lot about where things happen in the brain, but not how they happen, because this technique does not have a good time resolution. So basically we take images every second or so, but our thought processes happen much, much faster. So we decided that we wanted to record directly from nerve cells in the brain, and you can record at a millisecond scale, so in very fast order, to really understand how these processes of selective attention unfold over time. And that's what we have done during the last 10 years or so. And the first study that we did was actually to look at these old brain structures and to understand what they do in relation to these newer cortical areas that people had focused on for most of the time previously. And we actually identified one important function for them, and that is these structures are basically, they act like a conductor in an orchestra. If you think about the cortex, so the new parts, with their different areas that they have as people and musicians in an orchestra, then these old parts are basically the conductor that tell everybody when to do what. So, you know, all the important computations, if you like, they're all done there. They are done by the musicians playing the instrument, but they have to know when to come in, otherwise there will never be a piece of music. And that is what these old structures are doing. And that's at least one of the functions, that it's basically a temporal coordination to orchestrate what all these different parts in the cortex are doing to work together. And in our newest research, we have looked at the dimension of, again, a temporal dimension. So we are very much looking into what happens over time. And what scientists have done for most of the time, that's not only true for attention research, but for a lot of other research too, is they throw out the dimension of time. So, you know, you do a task and you do something, and then you have at the end of the task, let's say you detect somewhere a face. So you're sitting in front of the monitor and you get a display of faces and you look for a specific face. And then once you have detected that face, you hit a button. And this goes on over time and so on and so forth. And what scientists typically do is they record, they average across all of these different trials you do. Let's say you do 30 of those trials. Now, the interesting time is that your reaction time, so the time it takes you after you have detected the face to respond to it, will be different in every single of these 30 trials. But, as many scientists think that's not important, it's just random noise, biological systems are noisy, so probably has something to do with that. And we thought that, well, probably this has meaning actually, and it tells us something about how these underlying neural structures work. And so what we have looked at, again, in this context of the attention network that we're interested in, on how this network produces behavioral output. So something simple as I just described. You detect a stimulus, you react to that by pushing a button. And what we have found is that the network, if you look at it very carefully over time, what it's doing, it's setting up two alternating states. So one state is more characterized by taking in sensory information, and then the state switches to a state where you can more easily produce a motor response. And these two stages go back and forth. So if you happen to be in that more motor state, you can produce your reaction time more quickly than if you are just in that state where you're still processing sensory information and take that in. And we think that this is a really important characteristic of that attention network, and it gives us the ability to flexibly switch between either collecting more information from the environment because we have not quite found what we were looking for example, or to quickly, move into a more motor state where we actually produce a behavior. And we think that this may even have consequences for states where people are dealing or are struggling with an attention deficit. And as you know, I'm sure you've heard about that. That's quite common in school children. So that's attention deficit hyperactivity disorder. So we think that this may be basically a hallmark of a normally developed, of a neurotypical attention system. And we are looking right now actually in kids who struggle with ADHD to see how these attention rhythms operate, or if they operate in their brains, because if they don't, it would be relatively easy to basically get them, worked up again. You could do a music therapy, for instance, to kind of reinstate these rhythms. But that's ongoing work, so we don't know quite where it's going, but it could have some good, consequences for people who struggle with attention deficits. And that's quite a struggle, so I'm working a lot with those kids as well.
I see. So does this attention, our ability, like such as selective attention, differ between age groups?
Yes, that's another really great question. So attention function, like any other function, develops in the first place. And attention function, as other cognitive functions, involve very large brain networks. So there are different parts of the brain that have to come together to basically optimize that function. And that takes a while. We don't even know, with respect to attention function, how long it takes. But it may very well take into young adulthood for this function to be fully developed and fully optimized. That's another thing that we're looking at in the lab, to really understand what the development of that function is. But that's the first part. And during that development, things can go wrong, or they can get delayed, or something happens on the way. And that could then give rise to attention deficit disorders. Similarly, so then you can think about it, once that development is, concluded at some point, and that is individual from, person to person, we are in a steady state, and we are in that steady state, let's say in young adulthood, for a very long time. Attention function is very optimal for most people for a very long time. But then as we get older, it will decline. So it's going the opposite way. And that is really important to recognize as well, because, old people do all kinds of things where they have to be pretty alert, for instance, driving a car and so on. And so it's really important to monitor that as well, because it can get quite dangerous, once that function probably is too much degraded in an older person. This is also why it's for older people really, really important to exercise, their brains mentally, because most of that entails, training up or continuing training up, your attention system. You don't need that too much when you're younger, or when you're, a young adult and so on. But later on in life, that becomes really, really important, and I think people underestimate that. But it's a function that will degrade over time, and can still be trained up, though, so it's not to say it will degrade and we can't do anything about it. One can delay that degradation for a very, very long time, but it's a normal part of aging.
So do you think this is based off of genetics, or the idea of the nature versus nurture process, like the idea?
So the disorders that we see in neurodevelopment, so ADHD, has a genetic component. There's no question about that. So it very much runs in families, but also, many people are affected who do not have a family member, or it's not, they're the first, basically, at least for the diagnosis of that. So it's not necessarily, but you have a higher likelihood to be affected by ADHD if somebody in your family has ADHD as well. So there is a genetic component there. And there's also a genetic component that is involved with good brain health and brain aging later on. So some people just, see less cognitive decline, and others see more of that. And I think there is a very clear pattern that there is a genetic component as well. But genetics are just one thing, and I think the most important thing to know, especially for young people, is that a brain is what we call plastic. It can change all the time. It can learn new things all the time. And I think that power of a brain to transform all the time and to build, new connections, to build new skills is endless. And you can, as an old person, learn a new language. It may take a little bit longer than when you are, your age, but you can still learn it. And that's the important thing. And so I think to make that effort to be a long life learner, for instance, and to use your brain in the best ways possible is probably, the best advice you can, if you don't have good genes, well, you can make up for it. And if you have good genes, then you should, still keep good habits because they're not a guarantee for anything. So this is what I find actually one of the most intriguing things about the brain. So if I would start over as a brain scientist another time, I think I would start. I would look into learning, especially in learning during development. I find that very, very intriguing that our brains have an endless capacity to learn.
Right. So our ability of attention, does it have like, do the stimulus that we take in have different stages of processing, like different parts of the brain?
Yes, it has. So in that regard, actually, vision is really, really intriguing. So what happens with a visual stimulus in front of you or a scene, whatever you look at, is that it will first be decomposed into small components. So let's say in that scene behind me, you have a lot of, vertical and horizontal edges, right? You have some oblique ones, so on and so forth. So very early in the visual processing, there are actually filters that would only represent that information, all these vertical, horizontal, and oblique edges. It would completely decompose me into, probably a round form for my face or something, like that. And then all the colors there, I have these white earbuds and then my shirt here and so on and so forth, all the other colors there. But there would be basically color cells that are not interested in anything else than my blue shirt. There would be form cells that would be not interested in anything else than, the shape of my face and so on and so forth. And that's quite puzzling because the way how we perceive the world is, of course, as a coherent whole, as something that is composed of all these complex things in relation to each other. And so one of the big mysteries in vision is how that happens. So why do we filter first into all these different component parts, and then later on we know that there are cells that are face cells, or there are cells that would, code for this chair here I'm sitting on, and so on and so forth. So all these component parts will be put together. But what that transformation is that puts them all together and that gives us these kind of holistic view of the world, that is a big, big mystery.
Mm-hmm. So do you think there are any misconceptions in your field of study?
Misconceptions. What do you think? I mean, what do you, I'm not sure what a misconception mean, or what do you mean with a misconception?
So like, that some people a group of people might believe one thing about a certain idea or topic, which you think is not true.
I see. So you mean basically controversies
Yeah.
about some people believe this and other people believe this.
Mm-hmm.
Yeah, there are certainly, controversies that people have. And are there big controversies at the moment? I cannot actually really think of one, but let me just take that opportunity to probably just talk a little bit about controversies, because it's often difficult to understand actually for my students who I teach here at Princeton. So many people, and I think young people in particular, think about science as some form of truth. And that's actually not what science is at all. Science is a process. It's the search for some kind of truth. Though, even if we would find it, we would not know that that is the truth. That's the irony of it, right? Because you can see that only in relation to something else. So while we acquire knowledge that stays over time, and it may be close to that truth, what the controversies are all about is actually to fuel up that searching for the truth. So they are very, very useful. So I tell you about one controversy, and I don't even know whether that is sorted out by now or not, but it goes back 20 years. And that was at a time when some people in our field found that there is a region in the visual system, so in the system that codes for vision, it's in the back of the brain, that is specialized on faces.
Is it the fusiform face area?
It's the fusiform face area. That's exactly right.
Mm-hmm.
And that was a huge discovery. And then there was another group. So that was discovered by a researcher at MIT. Her name is Nancy Canvisher. And then there were other people who said, well, probably this is not so much of a face area, but it's an area that's actually an expertise area, because we are all face experts, because we can discriminate faces. They all really look alike, but we can, tell people apart just based on very small differences in those, facial patterns in front of us. And those people would, for instance, ask people who have a hobby in bird viewing, so they are bird experts. They can tell all these birds apart, really again by small differences. They ask guitar experts, car experts, people who can tell apart car models, thousands of them, and guitar models and so on. And whenever they would do that, this same area, the fusiform face area, would actually be engaged in that kind of discrimination of guitars or different car models and so on as well. So they concluded this is an expertise area, and we are all face experts, and this is why this area there is so interested in faces. So that is an example for such a controversy. And at the end of the day, it is not so much important whether that area is really specialized, particularly for faces, or whether it's an expertise area and we are all face experts. The important thing was that this whole controversy fueled, I think, 10 or 15 years of research into how objects, faces and other objects in the world, are represented in the human brain. And we just have learned so much about it. And I think without a controversy like that, it would just not have been so interesting to study that for, young people, students coming into the field. They thought, okay, what's interesting? What's hot here? And then they learned about this controversy and they said, oh yeah, we want to figure this out. We want to help with that. And so this is what a controversy is good and again, it's not so much about, finding the ground truths of, what exactly this area and its activation really means. And then the research went way, way beyond that. And I think that question almost became irrelevant at some point.
I see. So it's the discovery that's important, and also like I don't know, I feel like that those controversies are really what brings up people to like what you said, like want to find answers to questions. And I think these questions
Right.
I feel like more than just the subject itself, these little questions are what leads to big answers. So I think what you said was very important. All right, to sum it up, I just wanted to ask who or what was your inspiration to pursue your career, and any advice for students who want to be in a similar field to yours?
So I think my greatest inspiration was my PhD mentor. That was the person who transitioned me from philosophy to neuroscience. His name was Otto Creutzfeldt. And I think the mentor I had, so he was a wonderful mentor, and he really brought me he converted me to, become a neuroscientist. But the person who really showed me the way into the kind of research that I have done, how to mentor my students, how to be a good teacher, and so on, was my mentor at the National Institutes of Mental Health, Leslie Ungerleider. And she was really, really important for me because she was my first female role model. I just had never met, a female before who would, guide me. And that was really, really important because, I grew up in a time where there were very, very few female scientists. That has changed a little bit, but you have way, way too few. So we still have only about 20 to 25% of female scientists, neuroscientists in, at a more advanced career stage. So that was really important, I think, for who I became as a neuroscientist later on. Career advice for young people. I always tell my own students that they should follow their passion. And it doesn't matter what that is. It can be science or anything else, but they should try to find a passion for themselves and not so much listen to other people, including their parents, because parents sometimes have plans with their kids. And I understand that. I have kids too. But I think for young people, the most important thing is to discover something that in going forward will be fulfilling for a larger part of their life. And that is a very difficult process for young people, I think. But to really keep on searching for that. And once you have found that, to pursue it. And if you pursue it with a really great passion, you will be successful in what you're doing. And you will be able to take that to some interesting stage. And there's no question in my mind, at least, about that. So I would encourage you to find that for yourself, whatever it is. Once you have found it, reach out to people who you think might be helpful in fostering that and, guiding your way. Because, for some of you, it may be, you may not be surrounded by those people. So try to find them. And I think there's, in these days, so much information out there due to the fact that we have the internet. And so you just have to find the right information there.
I see.
I want to say one more thing, if I may. This is a little bit of an advertisement, but if you're interested in neuroscience or in other life sciences, a few colleagues of mine and myself, we have initiated about, I think, 7 or 8 years now, an open access journal for kids who are interested in science. It's called Frontiers for Young Minds. And the idea of Frontiers for Young Minds is that scientists are writing articles for kids about their original science, and the kids review it. And there are now a few hundred articles there. It's a wonderful source, I think, of information, but also of inspiration. We just launched a Nobel Prize collection. That's where you can find a starting point if you're looking for something new, probably. And then again, you could get in touch with those authors. These are all people who are interested in educating the next generation of young scientists, and they are passionate about that. And, they may be able to help you.
I see. Thank you so much for that. I really love that. Thank you for letting, I'll make sure to check that out. Thank you so much for coming today. I really appreciate you. That sums up my questions. Do you have anything last minute to add?
So how did you come to do this podcast? I think this is fantastic. And, interview all these people. That's such a wonderful thing to do.
Yeah, thank you. I actually started my passion for neuroscience through meditation, actually. So I really love meditation. And then I started taking classes in my high school because I was interested in the brain. I also work at a lab now virtually at UCI. And I'm also doing this along the side too. So I'm just exploring what I love.
That's great. And you know, the neural basis of meditation is very underexplored. So this would make for a really, really good graduate thesis. So you have found your thesis theme already, I think.
Yeah, thank you for asking that. Yeah, thank you so much for coming. It's really inspiring to meet women in STEM, especially. Uh, I think that's very motivating for me, especially. And
My
yeah,
pleasure.
I hope you have a good rest of your day. Take care of yourself.
You too. Thanks for having me.
Bye.